In this video tutorial, we'll cover value at risk. The relevant readings to this video are Value at Risk Chapter 5 and Chapter 7, Summary of the Variance of the CTE Estimator, ERM 102.12, ERM 105.12, and ERM 106.12. The tutorial will consist of the following topics, and we'll start with value at risk. Value at risk is the worst loss over a target horizon such that there is a low prescribed probability that the actual loss will be larger. The VaR is then the smallest loss in absolute value such that the probability that the loss is greater than VaR is less than or equal to 1 minus C, where C is our confidence level. So assume the current market value of the portfolio is 100 million. The standard deviation of the portfolio is 15%. Calculate the 99% 10-day VaR and assume 252 trading days per year. Well, the VaR would be equal to 100, our position size, multiplied by our 99% normal value, 2.33, multiplied by our sigma, 0.15, multiplied by the square root of 10 trading days over 252. And that gives us a value of 6.962207. Next, we'll cover absolute and relative VaR. Relative VaR is defined as the dollar loss relative to the mean on the horizon. So if you can think of a loss distribution here, if we have a loss distribution and we have 0 right here, if we calculate the expected value, call it here expected value of W, and we calculate our VaR, which is our quantile at some point in the loss distribution, the relative VaR would be the difference from this point to this point, or the expected value of W minus W star. The absolute VaR is the dollar loss relative to 0. So again, that would be the distance from here to here. So the absolute VaR is our 0 minus W star. So assume that we have 254 revenue values, and the average revenue is 5.1 million. Also assume that there are 11 observations to the left of negative 10 million and 15 to the left of negative 9 million. Calculate the relative 95% VaR and absolute 95% VaR. So here we have 254 observations. We want a 95% VaR. So 254 multiplied by 5% is our 12.7th observation. So we're given that there are 15 observations that are less than 9 million, and we're given 11 observations that are less than 10 million. So we're going to take a linear approximation, or we're going to take the value 15 minus 12.7 over 15 minus 11, multiplied by our $10 million value, because there's 11 here. So we want to linear interpolate between 11 and 15. So we get negative 10. Plus here we'll have 12.7 minus 11 divided by 15 minus 11. Times negative 9. This gives us negative 9.575 million. And this is our W star value. So our relative VaR is equal to our expected value of W minus our W star. So our expected revenue is 5.1 minus our W star. This gives us 14.675 million. Our absolute VaR is equal to 0 minus W star. So it's just 0 minus negative 9.575, so we get 9.575 million. Next, we'll move on to continuous probability distribution VaR. So VaR can also be derived from a probability distribution of the future portfolio value, call it F at W. We want to find the worst possible realization W star at a confidence level C. So we want to solve the integral. C equals the integral from W star to infinity of FW dW. Alternatively, we may also want the probability of a value lower than W star, or the probability that W is less than or equal to W star is equal to 1 minus C. So with that, we set 1 minus C equal to the integral from negative infinity to w star of fw dw. Now the area from negative infinity to w star must sum to p equals 1 minus c, and the number w star is called a quantile of the distribution. So you are told that the loss distribution is an exponential distribution as below. Calculate the 95% value at risk. So in this case, we want 1 minus 0.95 is 0.05 to be equal to the integral from w star to infinity of 0.2 e to the negative 0.2x dx. So we can solve this integral, and we get e. So we'll get negative e to the negative 0.2 times infinity. 1 over infinity is 0, so this will just be 0, minus negative e to the negative 0.2 w star. So we get 0.05 is equal to e to the negative 0.2 w star. So w star is equal to negative ln of 0.05 divided by 0.2, or 14.97866. Next, we'll cover parametric VaR. So if we assume the distribution of returns is normal, then the VaR can be derived directly from the portfolio standard deviation along with a multiplicative factor for the associated confidence level. So our relative VaR simplifies to W0, our position size, times alpha times sigma root delta t. Our absolute VaR is equal to W0 times alpha sigma root t, or delta t, minus mu delta t. So assume the standard deviation is 9.2 million. Calculate the 99% normal VaR and the 99% student t-VaR with 6 degrees of freedom, which corresponds to a t-value of 2.57. So our VaR, 99% normal, would be equal to our normal value for 99%, 2.33, multiplied by our sigma, multiplied by our root time. This gives us 21.436 million. And our VaR, 99% with the t distribution, would be equal to 2.57 multiplied by sigma root 1, and that gives us 23.644 million. Now, since the t distribution has more tail weight than the normal distribution, we see that the value at risk given is actually higher than the value at risk with normal, and this makes sense because the t distribution has more weight in the tail. Next, we'll cover portfolio VaR. So assume a portfolio return is a linear combination of the returns on the underlying assets. The weights are given by the relative amount invested at the beginning of the period, and the portfolio return from t to t plus 1 is the sum from I equals 1 to n of Wi Ri t plus 1, where n is the number of assets and Ri t plus 1 is the rate of return on asset I, and where Wi is the weight. So the rate of return is the change in the dollar value, or dollar return, scaled by the initial investment. And the portfolio return can be written in matrix notation as follows. So it's the sum of W1 to Wn times the R1 to Rn's. So we can write that with the matrix W1 to Wn and R1 to Rn, or just W transpose R. The portfolio expected return, or expected value of Rp, is simply the weighted value of our mu's, so Wi times mu I. And the variance can be written as the sum from I equals 1 to n of Wi squared sigma I squared plus 2 double sum from I equals 1 to n, j less than I to n, Wi Wj sigma ij. It's more convenient, though, to write this in matrix notation. So we'll let sigma be the covariance matrix. Then the portfolio variance, sigma p squared, can be written as W transpose sigma W, where W are our weights. Sigma is our covariance matrix with with variances down the diagonal and covariances on the off diagonals, and our weights over here transposed. Now we define C as the confidence level and W as the initial portfolio value. Then the portfolio VaR is equal to alpha sigma PW, or simply alpha times the square root of x transpose sigma x. So you're given the following portfolio of 3 assets. So we have 30, 20, and 50, and the covariance matrix as below. Calculate the 95% value at risk. So our VaR would be equal to 1.645 multiplied by the square root. Now we're going to multiply our matrix of x multiplied by our sigma matrix, where we have our variance terms down the diagonal and our covariance terms on the off diagonal. And then we're going to multiply that by our values of x again. Now we're taking the square root of this entire thing. Now this gives us 104.725928. Now just a reminder how to multiply matrices. What you're going to do is you're going to take this 30 multiplied by 0.25 plus 20 multiplied by 0.14 plus 50 times 0.36, and that gives you the first term. You're going to take this multiplied by the second column and this row multiplied by the third column, and you're going to get 3 values here. Then you take this value multiplied by the 30, this value multiplied by 20, and this value multiplied by 50. And that gives you the value in the middle. Then you take the square root and multiply by 1.645, and you get 104.7259. Next, we'll move on to diversified VaR versus undiversified VaR. Diversified VaR is the portfolio VaR taking into account diversification benefits between components. Individual VaR is the VaR of one component taken in isolation. So the individual VaR is like before, it's alpha sigma I wi w, where this can also be written as xi. Now the undiversified VaR is simply the sum of the individual VaRs, or the portfolio VaR when there is no short position and all correlations are unity. The diversification benefit is equal to our diversified VaR minus our undiversified VaR. And the level of diversification depends on the correlation, or the covariance, between assets. Covariance is a measure of the extent to which two variables move linearly together. The correlation coefficient is more convenient. It's a scale-free measure of linear dependence, and the correlation between two assets is equal to the covariance between 1 and 2 divided by the sigma 1 and sigma 2. So you're given the following portfolio of 3 assets. Using the covariance matrix below, calculate the individual VaRs and the associated diversification benefit for these 3 assets. The diversified VaR is given to be 104.7259. So first, we need to calculate the individual VaRs. So VaR A would be, in this case, 95% VaR, 1.645 multiplied by x, multiplied by our sigma here, which would be the square root of our variance. And this gives us 24.675. Our second VaR would be 1.645 multiplied by 20 multiplied by the square root of our second variance, 0.49. And that gives us 23.03. And our third variant or value at risk is 1.645 multiplied by 50 multiplied by the square root of 0.64. And that gives us 65.8. Now our diversification benefit is equal to our diversified VaR, our undiversified VaR, which would be the sum of these 3 components. So 65.8 plus 23.03 plus 24.675 minus 104.7259248. So our diversification benefit is simply equal to 8.7791. If the correlation between our assets is 0 in a two-asset model, the portfolio variance would then reduce to the square root of the sum of squared variances. Now, if you memorize, when you have 0 correlation, it's just the sum of the squareds, and then you take the square root. When the correlation is equal to 1 between all of our assets in the two-asset world, the value at risk would be equal to this sum of the individual value at risk. So value at risk 1 plus value at risk 2. Next, we'll move on to marginal VaR, incremental VaR, and component VaR. Marginal VaR is the change in portfolio VaR resulting from taking an additional dollar of exposure to a given component. It is also the partial or linear derivative with respect to the component position. So our marginal VaRi is equal to our partial derivative with respect to xi of our value at risk. And we can show that it's equal to alpha times the covariance of Ri Rp over sigma p. The marginal VaR is closely related to the beta, which measures the contribution of one security to portfolio risk. And beta I is equal to the covariance of Ri Rp over sigma p squared. We can show that that's equal to rho Ip over times sigma I over sigma p. In matrix notation, we can write beta as sigma w over w transpose sigma w. And the relationship between delta VaR, or marginal VaR, and beta is the following. Our marginal VaRi is equal to our total VaR divided by our total portfolio value w multiplied by our individual beta I. So we want to prove the following relationship. So we'll start with the left-hand side. We know that marginal VaR is equal to alpha sigma w over w prime sigma w square root of that. Our right-hand side, we have VaR over w multiplied by beta, which is equal to VaR over w multiplied by our beta, which is sigma w over w transpose sigma w. So now we can cancel a couple terms here, and we can cancel our w's. Now we know that VaR is equal to alpha times the square root of w prime sigma w multiplied by w multiplied by this factor over here. So now what are we left with? We're left with alpha, we're left with the sigma, we're left with the w, and then we have a square root of w prime sigma w divided by w prime sigma w. So on the denominator, we'll have the square root of w prime sigma w, which is equal to our left-hand side. So our left-hand side equals right-hand side, so that ends our proof. So find the 95% marginal VaR for the following portfolio. So our marginal VaR is equal to alpha sigma w over square root of w prime sigma w. So that's equal to 1.645 multiplied by our sigma matrix multiplied by w, which is 0.6.4, divided by the square root. So we'll put our w value, our sigma value, and finally our w value. So solving the matrix algebra, we get that equal to 0.80610038 and 0.9560722256. So now we want to find the beta of the portfolio of 3 stocks with weights 0.2, 0.3, and 0.5 respectively. We're given the covariance matrix below. So beta is equal to sigma w over w transpose sigma w. So we're going to write out our matrix for sigma. Multiplied by our weights, 0.2, 0.3, and 0.5. And then we're going to divide by our matrix of weights, multiplied by sigma here, multiplied by 0.2, 0.3, and 0.5. So if we solve this here, we get 0.272, 0.371, and 0.5096 divided by the denominator of 0.4205. So we can take each of these numbers divided by this, and we get the beta matrix of 0.6468488989, 0.8822829996, and 1.211890606. So next we'll cover incremental VaR. Incremental VaR is the change in VaR owing to a new position. It differs from the marginal VaR in that the amount added or subtracted can be large, in which case the VaR changes in a nonlinear fashion. So we would measure the VaR with the initial position, VaR P, and then again with the new position, VaR P plus A. The drawback to this, the approach requires a full revaluation of portfolio VaR, which can be quite time consuming, and it may not be practical for traders that need decisions quickly. So again, our full incremental VaR is VaR P plus A minus VaR P. Luckily, there's an approximation. The incremental VaR approximation is approximately equal to our marginal VaRs multiplied by our matrix A, which has our new position values. So assume we have two positions worth 100 and 300 with the covariance matrix below. We are considering adding $50 to position 1, so $100 will go to 150. So what is the approximate 95% incremental VaR for the new position? Well, first we need to calculate our marginal VaRs. So our marginal VaR again is alpha sigma W over the square root of W prime sigma W. So that's equal to 1.645 multiplied by our sigma matrix multiplied by our W values, which here we have 100, so W1 is 100 over 400, or 0.25, and then W2 would then be 1 minus that, or 0.75. So we'll put in our weights. And now we square root of our weights multiplied by our sigma matrix here, which is here, multiplied by our weights. So we get a marginal VaR matrix of 1.154415131 and 1.465444208. So now we have our marginal VaRs. So our I-VaR is approximately equal to our delta VaR times our A matrix. So we take our marginal VaRs, 1.465444208, and we multiply it by our matrix A. So our matrix A is we're going to increase position 1 by 50 and not change position 2. So then it's just 1.15 times 50 plus 1.46 times 0. So that gives us 57.72075,657. So by adding $50 to this position, we increase our value at risk by 57. Next, we'll cover the best hedge. We want to find the additional amount to invest in an asset in order to minimize the risk of the total portfolio. So when a new position or asset A is purchased, the portfolio changes to WP plus A is equal to W plus A. The variance of the dollar returns of the new portfolio would then be equal to sigma P squared W squared plus 2AW sigma IP plus A squared sigma I squared. We want to find the size of a new trade that leads to the lowest portfolio risk. So we can differentiate this above equation with respect to A. So differentiating this equation with respect to A gives us 2W sigma IP plus 2A sigma I squared. And then we set this equal to 0 and we solve for A. And the optimal solution is then A star equals negative W sigma IP over sigma I squared, which we can show is equal to negative W beta I sigma P squared sigma I squared over sigma I squared. So assume that the current portfolio variance is 0.25. The current portfolio value is 100. the new position to be added to the portfolio has a correlation with the portfolio of negative 0.2 and a variance of 0.09. Calculate the variance minimizing position. So A star is equal to negative W sigma IP over sigma I squared, which we can rewrite as negative W rho IP sigma I sigma P divided by sigma I squared, because the covariance is equal to the correlation multiplied by our individual sigmas. So we get negative 100 multiplied by our correlation of negative 0.2 multiplied by our two sigmas. So the first sigma I is going to be the square root of square root of 0.09 multiplied by the square root of 0.25, our portfolio variance, divided by 0.09, the variance of our new position. And this gives us 33.33333. So our optimal position in the new value A is $33.33. Next, we'll cover component VaR. So a partition of the portfolio VaR. So component VaR is a partition of the portfolio VaR that indicates how much the portfolio VaR would change, approximately if the given component was deleted. So by construction, the component VaR is summed to the portfolio VaR. So our sum of individual component VaRs, or CVaRs, should be equal to our portfolio VaR. This is useful when we want the individual VaRs to add up to the total VaR. We multiply the marginal VaRs by the current dollar position in asset or risk factor I. So our component VaR I is equal to our marginal VaR I times XI. Now remember, XI is simply WI times W, so our weight times our total value. So we can rearrange and we can show that it is equal to VaR times beta I WI. So the component VaR indicates how the portfolio VaR would change approximately if the component was deleted from the portfolio. So we can also calculate the percentage contribution of each CVaR to the total portfolio VaR, where the percentage contribution is equal to our individual CVaR over our VaR. This is invaluable for drill down exercises as it allows users to control their VaR. So suppose you have two positions with 60% in asset 1 and 40% in asset 2. The covariance matrix is as below. Calculate the 95% VaR for each asset. So we need to first calculate the beta, which is equal to sigma W over W prime sigma W. So we'll have 0.25, 0.24, 0.24, 0.36 multiplied by our weights, 0.6, 0.4, divided by 0.6, 0.4, 0.25, 0.24, 0.24, 0.36, and 0.6, 0.4, and that gives us values of 0.93607300427 and 1.095890411. Now our CVaR I is equal to our VaR WI beta I. Now what's our VaR? So our VaR is equal to 1.645 multiplied by the square root of our portfolio variance, which is 0.6, 0.4, multiplied by our covariance matrix, so we get a VaR of 0.8432932. So our CVaR1 is equal to 0.8432932 multiplied by our first weight, which is 0.6, multiplied by our first beta, 0.936073, some change. So we get 0.47360427. Our second CVaR is equal again to our VaR, 0.8432932, multiplied by our weight, multiplied by our second beta, 1.09589, and we get 0.3696627773. So now we have our two CVaRs, and just to check, if we take the sum of this value and this value, we get 0.8432932, which is equal to our VaR. So next we'll cover VaR for risk management and VaR for portfolio management. We can use marginal VaR to minimize the portfolio risk, and we can cut positions with the highest risk, and the point where the portfolio risk has reached a global minimum results in the marginal VaRs all being equal, where again our marginal VaR I is equal to our VaR over W times beta I. So we want to find the position such that all our marginal VaRs are equal. So you're told that the 95% VaR of a portfolio of two stocks is equal to 0.8432932. And you want to minimize the portfolio VaR by adjusting the weights of each of the two stocks. So to determine the new weights of each stock when minimized, and show that the marginal VaRs are now equal. Also calculate the new VaR of the portfolio. So first we need to calculate our marginal VaR. Now that's equal to alpha sigma W over the square root of W prime W. Now we want our two marginal VaRs to be equal. So we can show that that's equal to alpha times 0.25, 0.24, 0.24, 0.36, and then we have W1, weight 1, and weight 2. And we have on the bottom again W prime sigma W. Now we want marginal VaR 1 to be equal to marginal VaR 2. So we can solve for marginal VaR 1. So that would be alpha times, we're going to take 0.25 times W1 plus 0.24 times W2. So 0.25 W1 plus 0.24 W2 divided by the square root of W prime sigma W. We want that to be equal to our marginal VaR 2, which is 0.24 times W1 plus 0.236 times W2. So 0.24 W1 plus 0.36 W2. Again, divided by the square root of W prime sigma W. Now we're just going to solve for W1 and W2. So we can cancel these values. So we get 0.25 W1 plus 0.24 W2 is equal to this. So we can show that W1 is then equal to 12 W2. We also know that W1 plus W2 is equal to 1. So we have 12 W2 plus W2 is equal to 1. So 13 W2 is equal to 1. So W2 would then be equal to 1 over 13, and W1 would be 12 over 13. So the next thing we wanted to do in the question is show that the marginal VaRs are now equal. So our marginal VaR new would be equal to, let's assume 95% as above, 1.645 multiplied by our covariance matrix. Now we're going to use our new weights. So weight 1 is 12 over 13 and weight 2 is 1 over 13. In the denominator, we have the square root of our weights, 12 over 13, 1 over 13. And then we have our covariance matrix and our new weights. Solving this, we get 0.821233641 and 0.821233641. So our two marginal VaRs are equal. And finally, we want to calculate our new VaR. So it's going to be 1.645 multiplied by the square root of our new weights, our covariance matrix, and our new weights. And that gives us a value of 0.8212336. So you can see that the VaR has been reduced and is actually at the global minimum. We can also use VaR for portfolio management. So we can use marginal VaR to optimize our portfolio. We want to maximize the ratio of expected return to risk using the Sharpe ratio. And the Sharpe ratio is equal to the expected value of P divided by sigma P. Now we could also write this with VaR in the denominator instead of sigma p. We want to increase the portfolio expected return while minimizing the risk of the portfolio. We want the highest possible Sharpe ratio, and this is known as the optimal portfolio. At this point, the ratio of our expected returns to the marginal VaRs must be equal. So our EI over our marginal VaRs is constant. Alternatively, our EI, or expected value, divided by beta is also constant. So you are told that the 95% VaR of a portfolio of 2 stocks is 0.843292. Suppose that the expected return of the 2 stocks is 10% and 12%. The covariance matrix is as below. Determine the new weights such that the ratio of EI over beta I is the same for each asset. So we want 0.1 over sigma, we'll call this matrix, little matrix here, W1, over the square root of W1 sigma W, and I'll explain this in a second, to be equal to 0.12 divided by sigma W2, again another little matrix here notation, over W prime sigma W. Now what are these? Well, we'll fill in the values so we get 0.1. Now this sigma times W1, that's going to be sigma multiplied by our weight 1. So we have the weights here of, again, we're going to use W1 and W2. So this row 1 value here will be this row multiplied by these W1 factors. So 0.25 W1, 0.25 W1 plus 0.24 W2. We're going to divide that by W prime sigma W. We're going to set that equal to 0.2, and now this W2, this little factor here, is going to be this row multiplied by these weights. So 0.24 W1 plus 0.36 W2, again divided by W prime sigma W. So now we can cancel some things here and we can rearrange, and we can solve the following equation. 0.1 times 0.24 W1 plus 0.36 W2 is equal to 0.2 times 0.25 W1 plus 0.24 W2. So rearranging, we can show that W1 is equal to 1.2 W2. Again, we know that the sum of W1 and W2 is 1, so we can substitute in 1.2 W2 plus W2 is equal to 1. So we get W2 is equal to 1 over 2.2. That means that W1 must be equal to 1.2 over 2.2. So now let's calculate beta with our new weights. So we get our covariance matrix, 0.25, 0.24, 0.24, 0.36, multiplied by our new weights, 1.2 over 2.2 and 1 over 2.2, divided by 1.2 over 2.2 and 1 over 2.2, multiplied by our sigma matrix, multiplied by, again, our weights, and we get a beta matrix of 0.91666 repeating and 1.1. So now we wanted to show that EI over beta I is the same for both. So our first value would be 0.1 divided by 0.916666 repeating. Our second value would be 0.12 divided by 1.1. So we can show that that's equal to 0.109090909 and the same value, 0.109090909. So we've solved for our optimal weights that show that EI over BI or beta I is constant. So next we'll cover alternatives to value at risk. Expected shortfall, tail value at risk, and conditional tail expectation. Tail VaR considers both the probability and severity of losses that exceed a given quantile. It's the average of losses exceeding a given quantile. conditional tail expectation, or CTE, is set at the X% level and is denoted CTEX. It's the average cost of the highest 100 minus X% of the results. A note, CTEX is usually greater than X plus 1/2 of 100 minus X%. So in other words, CTE 90 is generally greater than the 95th percentile. Expected shortfall is the expected return on the portfolio in the worst alpha % of cases. So the expected shortfall is equal to the negative expected value of X, given that X is less than the negative value at risk. Shortcomings of these is that they consider only extreme losses. They don't consider the full distribution of values that you can draw from. Another alternative is conditional VaR. This is a weighted average of our value at risk and expected shortfall. For continuous distributions, the CVaR coincides with expected shortfall, but it does differ for non-continuous distributions. The modified VaR, or MVaR, considers the skewness and kurtosis in addition to the first two moments of the distribution, and utilizes the Cornish-Fisher expansion. This is appropriate if the portfolio's distribution is non-normal, yet relatively close to the Gaussian distribution. MVaR is not always a better alternative than traditional VaR, though. And finally, CoVaR. This is VaR conditioned on either the whole financial sector or a specific institution being in distress. It provides information relative to systemic risk and risk spillovers that occur. And our delta CoVaR is equal to our CoVaR minus VaR, which shows the marginal contribution of a particular institution to the overall systemic risk. So this measure could be a key tool for regulators in assessing the share of risk of each financial institution. Next, we'll cover variance and standard error of VaR and CTE. We can estimate confidence bands for a sigma-based quantile or parametric VaR using the following. Q hat is equal to alpha sigma hat, and the standard error of sigma hat is equal to sigma times the square root of 1 over 2t, and the standard error of Q hat is equal to the square root of c times 1 minus c over t times f of q squared. So if we assume a 95% one-day VaR with sigma of 9.2 million, 252 trading days in a year, what is the standard error of the VaR? Well, first we need our VaR. So our VaR, which is our Q hat, would be equal to 1.645 multiplied by our standard deviation, which is equal to 15.134. Our standard error of Q hat is equal to alpha sigma square root of 1 over 2t. So that's equal to 1.645 multiplied by 9.2 multiplied by the square root of 1 over 2 times 252. And this gives us a value of 0.671463. Now we'll cover the standard approach. So start with a random sample of x1 to xn of size n from the model, and then sort the sample in descending order to obtain the order statistics. So we get x1 is greater than x2 is greater than all the way to xn. We let alpha be equal to 1 minus k over n. Then the values for CTE and VaR are the following. CTE is the average value of our order statistics from I equals 1 to k. So it's our average of our worst k order statistics. And value at risk is simply our kth worst order statistic. So we have the following approximate variance and covariance formulas. The variance of our CTE is the variance of x given that x is greater or equal to the VaR plus alpha times CTE minus VaR squared over n times 1 minus alpha. Our variance of our value at risk is approximately equal to alpha times 1 minus alpha times divided by n times f at x at VaR squared. And our covariance is equal to alpha multiplied by CTE minus VaR over n times fx at VaR, where fx VaR is the probability density, fx at x, of a random variable x evaluated at the point that x is equal to our value at risk. CTE is easier to work with than VaR because it does not require us to use the probability density function fx. The variance of the CTE has two terms, the first term and the second term here. The first is the obvious extension of what happens when alpha equals 0, and the second term comes from the conditioning on the observation of the estimated VaR. So our VaR is equal to the expected value of our variance of CTE given VaR plus our variance of our expected value of CTE given VaR. So you are told that the 95% VaR is 25 million and the 95% CTE is 30 million. This is based on 1,000 observations. You're also told that the value of the underlying loss density evaluated at VaR is equal to 0.001. So, sorry, I'm going to change this. It's going to be equal to 0.01. Finally, you have your analyst calculate the variance of the loss given that the loss is greater than the value at risk, and she calculates it to be 5 million. Determine the variance of both the CTE and VaR estimate, as well as the covariance between the two. So what we're going to do here is we're going to write out we're going to solve for our variance of our CTE. Now that's equal to our variance of x, given that x is greater than our VaR, plus alpha times CTE minus VaR squared, divided by n times 1 minus alpha. So our variance was calculated to be 5, alpha is 0.95, CTE was 30, minus 25 squared, and we had 1,000 observations times 1 minus 0.95, so we get a value of 0.579. Our variance of our value at risk is equal to alpha times 1 minus alpha divided by n fx at VaR squared. Alpha 0.95, 1 minus 0.95 divided by 1,000 multiplied by our value here, which I'm going to say is 0.01, and we're going to square that. We get 0.475. And finally, our covariance between our CTE and VaR is equal to alpha multiplied by the difference between our CTE and VaR divided by n fx at VaR. So that's equal to 0.95 multiplied by the difference between our two statistics divided by 1,000 times 0.01, and that gives us 0.475. So you're told that F inverse at 0.95 is equal to 45, and F inverse at 0.94 is equal to 43. You're also told that for 1,000 data observations, the 95% estimate is 55 and the 95% VaR estimate is 45. Finally, you're told that the variance of the losses is greater than the variance of the loss is greater than the VaR is equal to 5. We want to calculate the FSC of the CTE and VaR estimates. Well, first, we need to know that FVaR can be approximated by our little value epsilon divided by Fn inverse at alpha minus Fn inverse at alpha minus epsilon. Now epsilon here we'll assume is 0.01, and we have our two values of 0.95 and 0.94, so we get 45 minus 43, so we get a value of 0.005 for F at VaR. Now our FSE at CTE is equal to the square root of our variance of x, given that x is greater than our VaR, plus alpha times our CTE minus VaR squared, divided by n times 1 minus alpha. So this will be equal to the square root of our value, or a variance of x given that x is greater than VaR, which in this case was 5, plus 0.95 times, here we have 55 minus 45 squared. We have 1,000 observations, 1 minus 0.95. So we get a value of root 2, or 1.414214. And our FSE of our VaR is equal to 1 over F at VaR multiplied by the square root of alpha times 1 minus alpha over n. So this is 1 over 0.005 square root of 0.95 times 1 minus 0.95 over 1,000. This is equal to 1.378405. So next we'll cover the limitations of VaR. So first, why not cover the advantages? The advantages of value at risk. VaR is a single number or a dollar figure. It's well understood across the industry. It's a simple approximation formulas exist. It works well for elliptical distributions, which include the normal and the t-distribution, and it's used by regulators such as Basel II and Solvency II. It also works well with Monte Carlo simulation and historical simulation. Some disadvantages. VaR is sufficient for stockholders if the level of loss exceeds VaR, the shareholders will lose their initial investment, but VaR is not sufficient from a regulator point of view. So if the loss exceeds VaR, then the policyholders are at risk, and this threatens the insurance industry and the regulator. VaR also fails subadditivity and is therefore not coherent. VaR is based on the assumption of normal returns, so it is coherent with the normal distribution. But with non-normal returns, VaR cannot adequately capture the tail risk. Historical VaR assumes that the past predicts the future and does not account for potential events that have not occurred historically. And VaR can also be exploited by traders and management, as it allows tail risk to be taken on and hidden from risk models. In other words, traders can sell products that have extreme tail risk that don't show up in the VaR models, such as credit default swaps, for example. Next, we'll cover coherence, which has 4 principles. The first is monotonicity. So if W1 is less than or equal to W2, then the risk measure at W1 must always be greater or equal to the risk measure at W2. So if Portfolio 1 has systematically lower returns than Portfolio 2 for all states, then its risk must be greater. The second is translation invariance. So rho of W plus K should be equal to rho of W minus K. So adding cash in the amount K to a portfolio should reduce its risk by K. Next is homogeneity. Rho of BW should be equal to B times rho W. So increasing the size of a portfolio by B should scale its risk by the same factor. And finally, subadditivity. Rho of W1 plus W2 should be less than or equal to rho W1 plus rho W2. So merging portfolios cannot increase risk. So we want to, sometimes the exam writers will give or ask you to provide an example that shows that VaR fails subadditivity. So here's an example where we have 11 loss points for X, or loss or gain points for X, and loss or gain points for Y. So we have the following loss and gains for X and Y, and then we can add the two and get X and Y. Now we can calculate the 90% VaR for each of X, Y, and the combination of X plus Y. So our 90% VaR with 11 data points would be our second highest loss. So here our highest is 23 and our second highest is 13. For Y, our highest loss would be negative 26. And the second highest is negative 7, so we get 7. And for X plus Y, our highest loss is negative 39, and our second highest loss is 30. So now we have our VaR of X plus Y is equal to 30, which is greater than 7 plus 13, 20, which is our sum of individual VaRs. This example also highlights a weakness of VaR for VaR Y. So you can see our VaR of Y is 7 and our VaR of X is 13. So we conclude that X is riskier. However, if you look at the total loss data points here, the largest loss actually occurs with Y. So VaR hides risks that are in the tail. So here, if you look at the total distribution, Y would actually appear to be riskier than X. But if you look at a VaR perspective, X appears to be riskier than X, or X appears to be riskier than Y. Here's another example that we can show. This one's easy to use on the exam. So all you have to remember is that for X1, you have 10 losses from 0, and then your 10th loss is 1. For x2, you have zeros, your 9th loss is 1, and your 10th is 0. And then you can add x1 and x2. So you get 1, 1 with zeros here. And then calculate the 85% VaR, which would correspond to the 9th value. So our 8th value here. So our VaR here would be, we'll go to the next slide. What we first want to do is we want to rank x1 and x2. So we rank x1 from 0 to our largest lost 1, x2 from 0 to our largest lost 1, and x1 plus x2 from 0 to our losses of 1 and 1. Now our 85% VaR would correspond to the 9th observations. So we get 0 and 0 for x1 and x2, and x1 plus x2 is 1. So we've shown that rho x1 plus rho x2 is equal to 0, and rho of x1 plus x2 is equal to 1, which is greater than 0. So then we have also shown that VaR fails subadditivity with this example. Well, this example would probably be easier to memorize for the exam, as you only need to memorize these two tables and then order the observations and show that VaR fails subadditivity. Finally, we'll use an example to show that standard deviation fails monotonicity. So we're given the following scenarios, x1 and x2, 10 observations from each scenario. And here, this one's pretty easy to remember too. x1 increases from 1 to 5, stays at 5, and then decreases to 1, where x2 is just level at 5. And our risk measure is simply expected value of L plus 2 times the standard deviation of L. So we can show by adding up these, dividing by 10, we can show the expected value of x is 3, and of course our expected value of x2 is 5. We can show that the standard deviation of x2 is 0 because there's no variation. And punching these into our calculator and using the stat mode on our calculator, we can quickly show that the standard deviation is 1.41. And we apply the risk measure that was given, and we get 5.43 for x1 and 5 for x2. Now the way that we show that it fails monotonicity is we know that x1 is always less than or equal to x2. But our risk measure of x1 is 5.83 and our risk measure of x2 is 5. So since x1 is always less than x2, we can show that our risk measure of x1 is actually greater than x2. So this fails monotonicity. Hope you've learned a lot in this lesson, and there are more lessons to come. Here we have 10 different video lessons, each covering important concepts, just like this video. After you're done watching this video, I recommend doing all the practice questions associated with the relevant readings at the beginning of the lesson.